myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, we are going to start the Microwave Measurement Part 4, which is the last topic of the Microwave Measurement section. So, in this section, we are continuing with the VSWR measurement, which we have ended in the last lecture. In the last lecture, we have come to the conclusion that VSWR measurement for less than 10 value can be done with the help of a VSWR meter, and for greater than 10 can be done with the help of a double minima method. So, we have to of course go through the VSWR meter. What is the VSWR meter? The VSWR meter is basically a high gain, high Q, low noise voltage amplifier, and it is tuned to a fixed frequency, and that is equal to 1 kilohertz, at which the microwave signal is modulated. The VSWR meter uses the detected signal out of the microwave detector as its input, which a VSWR meter basically takes the input as the detected signal which is coming up out of the microwave detector as the input. It amplifies that and provides the output as the calibrated voltmeter. The meter itself can be calibrated in the terms of VSWR. So, this is basically our VSWR. It directly measures the degree of mismatch between the transmission line and its load. So, what we are why we are using basically the term that is mismatch, because VSWR is equal to 1 minus rho upon 1 plus rho, and rho is our reflection coefficient which tells power reflected upon the power incident. That is why it is directly related to the reflection coefficient, which is basically showing the mismatch occurring, and because power reflection occurs only when there is a mismatch between the load and the input source, and if there is no mismatch, this power can't be reflected. All power get absorbed and there will be a 0 of the power reflected. That is why we can easily say, or we always used to say, that VSWR basically shows the degree of mismatch between the transmission line and its load. And now the VSWR meter actually is divided into the different types of ranges. So, and one pointer is attached. So, here the one pointer, and scale is different type. The first one is the voltage scale, and second one is the dB scale, third one is the VSWR scale, 10 millivolt basically VSWR minimum value, and then comes the expanded VSWR scale, and then expanded dB scale. So, in general terms basically we used to say that VSWR meter is divided into 3 type of major scale. First one is the VSWR scale, then second one is the expanded VSWR scale, and the third one is the expanded our dB scale in general. But this types of we can divide it further into this point: voltage in the terms of voltage, in the terms of a dB scale, in the terms of a VSWR scale, in the expanded VSWR scale, and the expanded dB scale. So, there are normally 3 scales we can generally say normally. First one is the normal SWR. It is used when VSWR is between 1 and 4, and for VSWRs between 3 and 10, the bottom of the normal SWR can be used. And for the expanded SWR, what is it? It is graduated to 1 to 1.3, and hence can be used whenever the VSWR is less than 1.3, because basically this expanded SWR comes into existence only because of that. Ki VSWR, we always design the system which is having a VSWR tending towards the 1. If the VSWR are much higher than the 1, then that system is not good for applying or for practical application. That is why any devices who is much more closer to 1 is further, whose that VSWR value is further calculated with the help of a expanded SWR. So, in general whenever we have a device whose SWR has to be calculated. So first of all we will show the normal SWR, and if its value is lying between this point, then it is okay, and if it is tending towards 1, then we are actually wanting the most precise result, then we will move towards the expanded SWR. And normally we measure the SWR in the terms of a dB. So, again a dB scale is attached, and there are various type of knobs are attached for the proper functioning and proper calibrating the SWR. Now comes the measurement of power. So, measurement of a power in the microwave can be done by in the terms of low power measurement, medium power measurement and the high power measurement. We measure the low power with the help of bolometric technique, and in that case the power ranges from the 0.01 milliwatt to 10 milliwatt, and medium power 10 milliwatt to 1 watt, and it can be measured with the help of a calorimeter technique. Then comes the high power measurement, which is greater than 10 watt, and we use the calorimeter watt meter for measuring the power. So, but in your syllabus only the measurement of high power is mentioned, that is why we are going to deal with the high power measurement only. So, power between 10 watt to 10 kilowatt is considered high, and it is measured by the calorimetric watt meter. With the watt, this meter are basically of two type, dry type and flow type. Dry type, it is named because it is uses a coaxial cable which is filled with a dielectric of high hysteresis loss, and flow type is named as it uses the water or oil or some liquid which is a good absorber of microwave. So, that is why it is named either dry type or a flow type. Now, the liquid fluid after flowing through the load experience a temperature rise due to microwave energy. Whenever fluid after flowing through the load, there is a temperature change. The difference between the temperature T1 of a known quantity of a liquid, when you are using a our watt meter and you are providing some liquid or something to it, in that case we already known with the temperature it has, and that temperature is noted and it will consider it as a T1, and when it is allowed to move towards the load, and after entering from the load the temperature changes to the T2 as it emerges out of the load. So, we are available with the T2 and the T1 value, and through this using the formula we are able to calculate the power, where P is equal to R Kp within bracket T2 minus T1 upon 4.18, where P is the power measured in the watt which we are actually requiring, R is the rate of flow which of a liquid which is already known to us, which we can easily determine before the liquid entering the load, specific heat of a liquid and specific gravity, and this T1 after T2 minus T1 is of course the temperature change in the degree centigrade. So, with the help of this we are able to measure the power. Now, in calorimeter measurement, heat losses do occur due to conduction and radiation, resulting in erroneous measurement of power. So, in this case basically we measure the power in the terms of temperature change, and heat losses also occur due to conduction and radiation. So, there may be some error arising out of this only. Errors in flow determination, calibration in the thermal inertia etc. all can also contribute to the error in measurement. Now comes the power meter. Power meter is a device which can measure the power directly and consists of a power sensor that converts the microwave power into a heat energy. The temperatures change, so provide an output current in the low frequency circuits that indicates power. So, basically here the role of a sensor which converts the microwave energy into the heat energy. The sensor used for microwave measurement are the Schottky barrier diode, bolometer and the thermocouple. These are the our devices which can be used for the sensors which are used for the power measurement. Now comes the microwave amplifiers. Microwave amplifier is a device for enhancing the output power signal of a microwave devices, usually by increasing the amplitude or height of the wave that directly relates to the power level. This is accomplished by channeling additional input power to the microwave devices, so that is microwave radiation carries more energy. And basically this our amplifiers are nothing but our klystron, our amplitron, our cross field amplifier, our gyrotron, about that which we have already discussed in the unit 3. All are the examples of our microwave amplifier. So, what is the main function of that? They actually enhance the microwave signal into the its higher values, that is why it is called as a microwave amplifier. Some types of oscillators are also existing in the our unit 3. For example, magnetron. Magnetron is an oscillator, so that does not comes in the section of a microwave amplifier. So, whenever you are going to write the examples or the working of a microwave amplifiers, so first of all examples are of course the gyrotron, the klystron, amplitron, etc. So, only take the amplifiers, not the oscillator. For example, magnetron, which is of the oscillator. Now, let us do some numerical related to the microwave measurement topic. So, what is given in here? Calculate the SWR of a transmission system operating at 10 gigahertz. Assume TE10. Why we are taking the TE10? Because this is the dominant mode in the case of a waveguide. Transmission inside a waveguide of dimension. The dimension of a waveguide is given 4 centimeter and cross 4 into 2.5 is the dimension of a waveguide which we are using. The distance between the two minimum power, that is D2 minus D1, is given, and it is equal to 1 mm on a slotted line, and you have to calculate the VSWR. So, these are the given parameters, and now you have to, with this given parameters, you are required to calculate the VSWR. So, what is given in this question? Given is frequency which is equal to 10 gigahertz, dimension of a waveguide, that is A is equal to 4 centimeter and B is equal to 2.5 centimeter, and as the double minima method. So, basically this question is dependent upon the double minima method. So, between two power points, minimum power points, that is equal to, we can easily understand as the example of a double minima method, and by the formula of the double minima method we can able to calculate the VSWR, and VSWR in that case is given by the formula lambda g upon pi d2 minus d1, and as already shown you that lambda g can be dependent upon the parameters of the waveguide which is used in our bench while we are measuring the VSWR, and d2 minus d1 value that is already given, that is 1 mm. So, we are now going to calculate the lambda g. So, for calculating the lambda g, what do we have to know? We have to know lambda naught and lambda c. Lambda naught is basically our operating wavelength, and operating frequency is given to you. What is the operating frequency? 10 gigahertz. So, if you are available with the frequency, we can easily find out the wavelength. So, what will be the expression of wavelength in that case? C by f. So, this will give you operating wavelength. So, what is the C is basically the speed of the light, and it is given by 3 into 10 to the power of 10 in the case of a centimeter, not the meter, and frequency is 10 into 10 to the power of 9, that is equal to 3 centimeter. So, we are able to have the lambda naught, and we know for TE10 our lambda c is equal to 2a. This is formula is already available with you. So, and a value is known to you, that is equal to 4 centimeter. So, you are able to get the lambda c is equal to 2a is equal to 2 cross 4 is equal to 8 centimeter, and when substituting that is lambda naught equal to 3, and because since all the expression value is in the terms of centimeter, that is why we are not writing anything else here. 1 under root 1 minus 3 upon 8 square, 8 lambda c which is obtained here, we are able to get the value of lambda g is equal to 3.236 centimeter, and now we are substituting in the expression of a VSWR using double minima method. Lambda g is equal to 3.236, pi value, standard value 1 into 10 to the power minus 9, and we are able to get the VSWR 10.3, and we know that for measuring the VSWR greater than 10 we use the double minima method. Now comes the second numerical. What is this? Two identical 3 dB directional couplers are used. So, what is the, can you guess which type of method we are using? Impedance measurement using the reflectometer, and we are also use that in the case of a measurement of our reflection coefficient VSWR. Two identical 3 dB directional couplers are used to sample incident and reflected waveguide. VSWR is equal to 2 and the output of the coupler sampling incident power is 4.5 milliwatt. What is the value of the reflected power? So, we know that the VSWR is equal to 1 plus rho upon 1 minus rho, which is equal to 2. So, with this help we are able to get the value of, by solving this, we can directly able to solve it 1 plus rho 2 by using the cross multiplication method, and continue solving we are able to calculate the value of reflection coefficient, that is rho is equal to 0.333. And now the second thing which is given here, that is 30 dB directional coupler. That means the coupled output should be equal to 30. So, that thing is used here. Coupled output C is equal to 10 log pi upon Pf, and that is equal to 30. So, by solving it, pi upon this 10 this side, just for your purpose, log pi by Pf is equal to 30 upon 10 is equal to 3. And when we want to remove the log, what we are doing? We are basically pi by Pf is equal to, this is the example of base 10 log. Basically whenever we write the log, it means base 10. So, this base 10 and 3 to the power. So, we have pi upon Pf is equal to 10 to the power 3. So, now we have to calculate the Pf. Pf is equal to pi upon 10 to the power of 3, that if so, here we are able to get the pi upon 1000. And the next thing which is provided to us in the question, that is output of the coupler sampling incident power. Output of the coupler sampling incident power. So, what is the coupled sampling? Output of the coupler sampling, that is of course, if you remember, that is in the terms of 1000. Now, we have 4.5 milliwatt, and that is equal to pi upon 1000. So, by this condition we are able to get the our pi, which is equal to 4.5 watt. Now, as the reflectometer reading shows, rho is equal to under root PR upon 1000 under root divided by pi upon 1000. If you are remembering, this is basically our reflectometer reading. So, 1000 upon 1000 get cancelled, and we are available with under root PR upon PI. So, for solving it, we are squaring the both side and we are getting rho square upon PR upon PI. So, of course, with this help we are able to get the PR is equal to rho square PI, and rho already solved, and it is equal to 0.333 and PI is equal to 4.5 watt, and on substituting we are able to get 0.499 watt as the reflected power. So, for solving this equation we have to one by one solve all the parameters which is required for getting the final expression. So, for all the microwave measurement questions, numericals, you have to first analyze which type of devices are used. and then only you are able to get the correct measurement. So, in the first case we are having the difference between the two distance we are able to get, that is d2 minus d1 is available in the given section, given parameters which are available with us. So, we can easily analyze, that is a double minima method. Or here in this question what is asked in the two directional couplers are used, in the reflectometer we use the two directional couplers, and reflected power, incident power are mentioned here. So, we can easily say that is the measurement using reflectometer. Now comes the third question. The two directional coupler 20 dB in a guide to sample the incident and reflected power. The output of our two couplers are 3 milliwatt and 0.1 milliwatt respectively. What is the value of VSWR? So, just the reverse of the question which we have already done. What is available with this? It is saying that output of the two couplers. So, output of the two couplers is basically what? Pi upon 1000 is equal to 3 milliwatt and PR upon 1000 is equal to 0.1 milliwatt. It is given. So, we have to basically, whenever we say that output of the two couplers, do not get confused that it will be Pi, basically it is a Pi upon 1000. Sorry, Pi upon 100, Pi upon 100 and PR upon 100. So, it is Pi upon 100 is 3 milliwatt and PR upon 100 is 0.1 milliwatt. So, we can easily have the value of Pi and PR from that, and when we take a reflection, we want to calculate the reflection coefficient. So, what we are basically doing, we are solving it and we are getting this as this one, our 0.19816, and when we are have the value of our rho, that is our reflection coefficient, we can directly substitute that in the VSWR expression, that is VSWR expression is equal to 1 plus rho upon 1 minus rho, which is equal to 1 plus 0.1816 upon 1 minus 0.1816. So, here comes the end of our microwave measurement. So, if you are not remembering, rho is equal to what? Under root PR upon Pi actually. So, PR is equal to 10 milliwatt and Pi is equal to 300 milliwatt, and we are going to solve it and have it. So, here comes the end of the microwave measurement topic, and the numericals are endless for this, and in this section you are able to get the numerical also and different measurements based questions. And if you want to have the practical knowledge of this microwave measurement, so kindly go to your labs available in your college and ask the instructor or the faculty present there to show you the method, because all the things which we have studied in the microwave measurement section in the theory part can be analyzed, can be viewed in the labs also. And if you are able to 100% familiar with the theory part, then you are get that practically demonstrated in your lab. And if you are get the practical knowledge in your lab, then of course you are able to understand the theory better. So, after studying this particular topic, all of you should visit your labs available in the college, so and ask the instructor there to show you the microwave measurement, different methods of the microwave measurement. Here you are able to, there you will able to see the VSWR, there you are able to measure the our double minima method, we can easily calculate. There we will able to calculate various almost everything which we have studied here. So, all the best to all of you. Thank you for attending today's class.